Okay, we're going to work a problem that involves some point particle system calculations and some real system calculations. And the problem says, well, first off, it says that friction forces are sometimes, or conceived as always slowing an object down, but this is not always true. If you place a box of mass m on a moving horizontal conveyor belt, the friction force of the belt acting on the bottom of the box speeds up the box. At first, there is some slipping, which comes into play later in the problem, until the speed of the box catches up to the v, or velocity, of the belt. The coefficient of friction between the box and the belt is mu, and I actually made it like mu kinetic because it's here we go. Okay, here is our system box on a conveyor belt. The m is the mass. The force up is the normal force. The force down, mg, is the gravitational force. And the frictional force is in the same direction as our velocity over here. Okay, and it says what is, for the first section, it wants to know what is the distance, and we're going to use d, distance, relative to the floor that the box moves before reaching the final speed v, and it wants you to come from an energy argument. Oh, wait a minute, that's for the next part. Okay, anyways, it wants to know the speed. Okay. So, if we find our equation, mu times the normal force, and set that equal to the frictional force, it's a good start. Okay, and we have the sum of forces in the y direction now are the normal minus the gravitational force, and that means that the gravitational force equals the normal force because it's just sitting there on the conveyor belt, moving at a steady acceleration. And so we can go back to our frictional equation, replace the normal force with mg, and now we have the coefficient, frictional coefficient, times mg for our frictional force. And here we go from our energy point particle system equation equals F times delta R center mass, and that will equal the kinetic translational, change in the kinetic translational. So we can replace F dot R with our frictional force times D and set that equal to our equation for translational kinetic energy, 1/2 mv squared, and this is the change in velocity. And since the initial velocity is the change is 0, we just 1/2 mv squared, do our algebra, and you will get that d equals the final velocity squared over 2 times the coefficient friction times g, gravity, because we're assuming this is on Earth. All right, and that's the distance it moves. Anyways, so at the final velocity. Okay. The second question asks how much time does it take for the box to reach its final speed, and to analyze this point we're going to sum up the forces in the x direction, which is just the frictional force, and we're going to set that to Newton's first for force, mass times acceleration, right there, and just do our algebra. The masses will cancel out, right, and we can solve for focus. We can solve for acceleration. We can break acceleration down, and you will end up getting that the time equals the velocity divided by mu g. All right, and that's the time that it takes for this box to reach its final speed. So now we have the distance it moved when it reaches its final speed, and the time it moved, the time it takes it to reach the final speed. And the last section simply will solve for the change in internal energy, so as to neglect the thermal energy when making this equation. It's kind of a tip-off that you're going to need to use it to analyze it from the real system and not the point particle system like we did in the previous two. Math is, this is getting long, but anyways, so delta E real equals the change in kinetic translational plus the change in kinetic rotational plus the change in internal, and that equals F dot delta R of the force. We already solved F. Delta R will be D plus a little bit of slippage distance. We'll treat our rotational energy like it's a solid disk, and so we will get 1/2 moment of inertia omega squared, and we already solved for K translational. It's mu mgd. And anyways, just a little bit of simple algebra later, we have our eternal energy calculation.